So while we are getting the slides up, I'm Subhash Shinde. I'm the Associate Director for ND Energy. And I would like to welcome Professor Alissa Park. He's our next speaker. Professor Park holds the Lenfest Chair in Applied Climate Science in the Department of Earth and Environmental Engineering, Columbia University. She's also the director of the Lenfest Center for Sustainable Energy at the Earth Institute. Today, her talk is titled Towards Sustainable Energy and Materials, Carbon Capture, Utilization, and Storage. Professor Park.
Thank you. Thank you for the kind introduction. And Rachel, I really enjoyed your talk. And once in a while, I do give a talk with somebody from LanzaTech, and I think we have a good discussion going back to back. So I'm glad I'm giving a talk right after yours. Good. So as he mentioned, I'm at Columbia University. I'm going to talk about carbon capture and utilization and storage. And hopefully with this audience, I do not need to talk about climate change, right? So let's not go there. And with the recent election, hopefully we don't need to ever go there again. So having said that, we are now linking the climate change with the way we use our resources and producing energy. And that has been a big question how to address this for a long time. And as Rachel mentioned, we've been working in this area of mitigating climate change last 3-4 decades. So it's not a short period of time. And a lot of times when you're talking about carbon management, people are kind of considering this area of research as bridge technology. We always thought that we're going to get to the renewable energy quickly, maybe a few decades. We just need to survive until then. I think more and more what we learn and what we just saw as well is that this bridge will be very long. It's not going to be 10 or 20 years, it will be generations long, which means that the way we use or manipulate carbon-based materials and fuels and so on should be done correctly. At the same time, there was a very interesting discussion at Paris Agreement, and I think we are joining back on Paris Agreement. At the time, there were a bunch of billionaires got together and said, well, this is the problem we should have solved today, so why don't I put a lot of effort into this and we can do the demonstration. But there was another interesting discussion happen. It was a Mission Innovation, which is the collection of governments got together and ministries of 23 countries and EU got together, basically entire world, and said that this challenge is not a short bridge, which meaning that not only we need to demonstrate the technology we have today, but the technology we're going to have at 2050, 2100, it may not exist today, which means that we need to advance fundamental science in this area, not only developing technology. In my opinion, this is a really big statement. When was the last time the entire world got together and saying, let's advance fundamental science together? And that was really nice. And in order to do that, Mission Innovation identified 8 theme areas. They initially started with 7 theme areas, and then later they added hydrogen as the 8th member. So as you can see, there are a lot of things you recognize, I'm sure, and you were talking about it, Peter was talking about at the beginning of the introduction of your center, here that smart grid or sustainable biofuel, converting sunlight, or these are something you already know somewhat. But interestingly, these fundamental science behind or engineering behind these are really interconnected. So for example, you can see that you can have carbon capture and storage and maybe make a whole new generation of building materials, which provides a lot better heat management within the building. At the same time, we can convert biomass into fuels like LanzaTech does, and at the same time, we can do CCS perhaps, and we can also make hydrogen. We can also convert sunlight and then convert CO2 using that electricity from solar energy, and then provide the energy storage for off-grid. So there are many interesting ideas we can come up with, but at the end of the day, the main key area was that the message was we do need to advance the fundamental science in these areas. So each of these buckets were asked to have a workshop, and I was very excited when I was selected to lead the discussion on carbon capture, utilization, and storage. One of the things I want to point it out is that here there are different flags. These are the countries that are leading each of the theme areas, each of the challenge. Do you see American flag? We used to be right here. Before it was Saudi Arabia and United States, but we dropped out about 2018, and that's when UK and Mexico stepped in. So hopefully in future, we'll have a lot more leadership, global leadership in these areas. So that workshop happened in fall 2000, and this report as a statement on how to achieve carbon management in order to mitigate climate. And this is the online version which you can access, and I think it would be a good read for you, any of the young scientists, to go into this area. So having said that, there was a lot of discussion about 2013 that people were getting concerned in the area, people who've been working on CCUS area. The reason was that was about time we really funded a lot of research on carbon capture and storage, and we really worked hard, at least more than 2 decades. But we did not have commercialized the CO2 capture or storage units until then. So when IPCC and national academies were coming up with these two reports, people were quite concerned. We thought that maybe the message will be, well, we're way too late. This will be way too expensive. Maybe we should give up and do something else. But their message was quite different, and that was interesting. This is what they said. We need substantial multi-century climate change commitment created by past, present, and future emissions of carbon dioxide. This statement doesn't seem to be a huge statement, but in fact, this is a really big statement when you think about it. So when I tell you that you have some chemical plant, and then this chemical plant emits something you don't want to emit into that environment, easiest thing to do, or first thing to do, you will do is that you go to emission point, which is like a chimney, and then you will install something, scrub out whatever pollutant you don't want it to go into the atmosphere. So if you're doing CO2 CCS, you're basically addressing present and future emissions of CO2 as soon as you install that. But how about the past? This is a 4-letter word, so it doesn't seem to be that big, past. What happened to our historic emissions of carbon dioxide? Although we complain about the increasing concentration of CO2 in atmosphere, this is still 410 parts per million in atmosphere. So unfortunately, we've been diluting CO2 into the atmosphere. And that's how we were dealing with emissions of the CO2 before we started worrying about climate change. So at this time, the total quantity of CO2 in atmosphere is making climate change. At the same time, going back to the historically emitted CO2 in atmosphere and picking them up, it is a huge challenge because of the low concentration of carbon dioxide. So the fact that they're saying this statement is amazing because they're saying not only we agree that we need to stop the emission and do it better, but at the same time, we're going to even go into the history and picking up the CO2 we emitted for decades, which calls for negative emission technologies. So it goes to 0 all the way and then negative. I think there's a lot of discussion between whether negative emission technologies will distract the 0 emission technology. People argue that we should go to 0 before we go to negative. I agree. It shouldn't be one or the other. Basically, this is telling you that we should do it all, in my opinion. So what are some of the options for negative emission technologies? At the end of the day, the word negative implies whatever you do, new technology you have, you need to lower negative direction of CO2 concentration in atmosphere. Means that whatever CO2 in atmosphere has to be captured and put it away and never goes back out into the atmosphere. If you're circulating above the ground, that's 0 emission or closing the carbon carbon cycle. So if you really want to be truly negative, you have to capture CO2 throughout whatever conversion or utilization you're doing and store eventually with permanency, which we can define so many ways. So here are some of the questions. One way to do it is a biomass. Trees and plants been doing this forever, and they basically capture CO2 from atmosphere, and the energy source is sunlight, and then convert it to solid biomass, and then you can use this as a carbon neutral energy source. And if you just release the CO2 back out, that's zero emission, because you capture CO2 from air and then store the energy of sunlight into biomass, and then you're releasing back. But what if we capture CO2 from biomass burning power plants and then store back? Then now you create the negative emission. You can replace actual trees with artificial tree, like a direct air capture system, which is chemically capturing CO2 from atmosphere, and then you can also store CO2. But this manipulation, people start to think that, well, if you can go to the lowest concentration of CO2 and capturing them, we can perhaps looking at this whole overall scheme to make a much better cycle of carbon throughout our materials and chemicals and fuel system, and at the same time, make sure that climate change is mitigated. So having said that, maybe I can go back a little bit and talk about where we started in CCUS research. First, we worked on point source capture, how to capture CO2 from coal-fired power plant. That was one of the big targets from the beginning of CCUS research for a long time. Without going through all the chemistries, this is the National Energy Technology Lab comes up with this map once in a while, and I don't think it changed much over the last 10 years or so. Obviously, these are the technologies more viewed as futuristic, compared to the technology like amine-based solvents are the ones we know how to do today. We actually have a lot of know-how in these amine-based materials. So amine is base, CO2 is acidic gas. Very similar to acidic gas such as hydrogen sulfide, you can capture these materials very easily. So if you combine them together, you have acid-base reaction, and in that binding energy will be lowering the material into lower energy level, and that captures quite effectively and selectively with a quite fast rate. But once you capture, you don't want to throw out that CO2-loaded amine solution out the door, because every material we use have a carbon footprint, an environmental footprint, and energy footprint. So any environmental control technologies, you are mostly kind of doing catch and release. You have to catch and release so that the lean solvent has to go back and pick up another set of CO2. So that becomes interesting, because how much energy can we put in to release the CO2 back and regenerate this solvent? So when we were talking about CO2 capture technology, as shown in the right-hand side, you can actually have two reactors. At lower temperature, you add the flue gas in, you can use amine solvent, trickle down from the top, and you can capture CO2 effectively, so that now liquid is fully loaded with CO2, will be going to solvent regeneration reactor. Now, because you're going back up the hill to release CO2, you have to provide energy to this system. You can do it either temperature swing or pressure swing or combination of both. Generally, we do both of that. So then at the time, when you look at this overall system, we can exactly calculate how much CO2 can be captured per ton of the solvent materials or per hour and all those things. But we have to kind of go back and think about, well, this doesn't operate for free. Energy has to come from somewhere. So earlier discussion we had was, if we install this technology in the coal-fired power plant, what will be the reduction in power plant capacity, or do we need to burn more fuel? Either way, you have to do that. And the estimation was your power plant efficiency will be reduced by 1/3. That's really significant. So people are getting really concerned. One of the reasons the power plant efficiency is going down by 1/3 is because these solvent materials cannot be used as a pure form. You have to dilute it in water. If water was a good solvent for CO2, of course, we'll just use water. But unfortunately, it's not. That's why we had to put amine. So that only Sorry about hearing all the New York sound, right? So then having only maximum 30 weight percent of MEA means that 70 to 85% water is going along the ride. You have to heat it up to 120, 140 degrees C and cooling it down. That whole parasitic energy consumption was reducing power plant efficiency by 1/3. But still, we know this technology more than anything, so that a lot of us are working in this area. In the United States, our first large-scale demonstration for CO2 capture system happened at Petronova project site in Houston. This is basically CO2 capture and solvent regeneration units, not even a full scale. You can see how big this scale has to be. It was working well. I heard that it's now on hold for now, but we are really looking forward to the data they're gonna provide us and showing us how we can do this in a large scale. But at the same time, because all the challenge with water, people start looking into other type of solvent. So for example, these are some of the water-lean or waterless solvents people have been looking at. Without going into too much detail, in fact, ionic liquid was actually developed by University of Notre Dame. Your Joan Brennicky, who you lost to UT Austin, very sadly, she's the pioneer, and at McLean in chemical engineering, they've been discovering how to tune this ionic liquid to make one of the best CO2 capture materials without having any water involved. Cobalt is done by PNNL, and we also worked on something similar to ionic liquid we call NOMS. It's a nanoparticle organic hybrid materials. Basically, we tether polymer onto nanoparticle. By doing so, we can really improve the thermal stability. So one of the key characteristics we really liked about ionic liquid is very flexible, wide range of a chemical mix you can have. So many combinations. So chemical tunability is amazing, but also it has almost zero vapor pressure. You can heat it up, cooling it down. We don't need to worry about fugitive emissions of solvent. There's so many good things going on with this material. But so when we looked at the NOMS, we were hoping to design this material very similarly behaving as ionic liquid. So this is some of the example of our data with our NOMS material. If you untether the polymer, just a regular polymer you start with, there's a sharp decrease, which means it degrades about 200 degrees C. As soon as you make NOMS by tethering them onto nanoparticle, you can really improve its thermal stability, so that you can see it can be operating safely 100 to 150 degrees higher temperature than we were hoping, we were starting with, which is good. The reason this is important is whenever you have technologies like a CO2 capture, initial investment on price of the solvent should go into the NOMS, which means that you should be able to operate this material thousands and thousands cycles, or even 10,000s, for this to be economical. So we didn't go to 10,000. We stopped at 100 cycles, but as you can see, NOMS is very thermally stable and very promising compared to this material, which is untethered polymer. So we start to see a lot of good things about NOMS with the promising results with that. We can perhaps use this multiple cycles in industry. So next thing we had to do was all these polymer chains, we wanted to put the functional groups like amine as much as possible, because more amine functional groups you'll have more higher improved CO2 capture capacity as we expected. All these were really fantastic. So it was a really good result. So we were hoping that, yeah, why don't we try to make this in the large scale? Then next thing we had to measure was viscosity, because these are still liquid-like material. Although there are a lot of nanoparticles, there's a tether with polymer with the right grafting density and the length so that it behaves like a liquid. So if you look here, this is the viscosity of MEA solvent, which is very close to water, very easy to pump it around. You saw the large CO2 capture tower, we need to pump the liquid through. There was no problem. The second groups are ionic liquids developed by Notre Dame group. And these are the materials at the top, NOMS material we developed. These are relatively old data in 2013, just early on when we were looking at the initial draft of these materials, designs of these materials. And John and everybody else were really brave and say, well, this is high to pump it around, but I can reduce it. And actually they achieved it by controlling hydrogen bonding. It was really amazing research. But we looked at our material and note that this is log plot. So then this is really hugely high viscosity. So we start thinking that, well, it is a challenge, but it can be opportunity. Why do we care about viscosity so much? Because we keep thinking about the reactor design, which is already out there. Perhaps we should think about a whole another design of the reactors. So in order to increase the interfacial area and overcome the challenge of moving all this sticky honey-like fluid around, we decided that why don't we chop up all this honey-like sticky fluid and package them? So we started collaborating with the Lawrence Livermore National Lab and developed this microfluidic device, which creates droplet instead of droplet. So the blue material right here is basically the NOMS material we developed, and then white material here is a UV curable polymer. So once you create the droplet instead of droplet, second stage will UV cure only the UV curable polymer, which now create the solid barrier as a shell, but still gas permeable. Now we have liquid encapsulated inside this shell. We don't need to design a reactor for the liquid solvent. So now you get a benefit of a liquid solvent and solid sorbent in the system. So this is some of the pictures of our actual solvent system. So these are blue, we just put the blue dye to show where our material is. You can do single core, multi-core. And as you do this gas permeable shell will allow a lot of CO2 to go through with a minimum pressure drop. So this is our kinetic data. If you start with the highly viscous fluid, you have a good capture capacity, but it really takes a long time. As soon as you encapsulate them, you can really shorten the time to capture CO2. And now, interestingly, because this material, this shell can protect this high viscosity solvent, you can actually put this outside, even in the environment. So you already saw this picture. I apologize for the car sound, but this is a Climeworks in Switzerland for direct air capture unit. So what these units do is they're letting a lot of air go through, because in order to pick up CO2 from 410 or 400 parts per million, you need to process a lot more air than flue gas stream in the power plants. So you're trying to capture CO2 at much lower concentration, and you are not going to try to capture 95+% of CO2. You are trying to do at least 60. So targets are very different, and also the material property you require is very different. You cannot use solvent system in such a system because you will dry up in air. So that having that encapsulated liquid does not have any vapor pressure became a lot of interesting opportunity in this area. So switching the gear a little bit, what would you do once you capture CO2? It can be capturing CO2 directly from air, or it could be steel plant, it could be coal-fired power plant, or natural gas-fired power plant, or even waste-to-energy plant. At the end of the day, if you do care about climate change, we have to store. Today, I'm talking about. Not in the future, but today. Because we have so much of CO2 emission that we cannot utilize all the CO2 we emit today. So it is important for us to have negative emission by putting a lot of CO2 in the geological formations, and that's important. But at the same time, the utilization kind of provides a kind of unique opportunity. And as Rachel mentioned, if you look around your room right now, if I ask you to pick one item does not have carbon in it, it would be very hard, including yourself. You have a lot of carbon in you. So when you think about it, carbon has to come from somewhere. So best carbon management for the long term for history of humanity will be do not take any more fossil carbon out of the ground. And if you can still have these chemicals and fuels and materials, wouldn't it be great? So decarbonization of power sector is okay, but decarbonizing any of these materials and chemicals and fuels is impossible because without carbon, they don't exist. So in a sense that you have to defossilize these chemicals and materials. And that's different questions. Of course, we can all wear cotton only and then do bio-derived materials. That's one way to do it. But at the same time, if we can start from CO2, maybe we can also complete the cycle and then create a new carbon economy. So now there's a lot of discussion on carbon recycling or upcycling scheme. This is the, again, US Department of Energy, NETL came up with. Basically what they said was, okay, if we capture CO2, you can make anything you want, which is true. We have a lot of smart people making a lot of catalysts and reaction pathways, making any material you want to make. Unfortunately, it costs you, right? It will cost you energy and even water footprint, and it will be environmental footprint. All those considerations has to go in to see that whether that was the right product to make, or is that the right pathways to do it. Another thing is, until now, capturing CO2 was dictated by storage. So when you think about it, if you're working on CO2 capture area, when you ask for what is your CO2 capture price per ton basis, that usually includes the compression cost. Because between CO2 capture and storage, there's a transportation, that little arrow. So in order to do transportation, you want a minimum volume, right? And also the high purity, so usually, and high pressure. So you need to capture CO2 with the pure form and least amount of water, almost you have to fully dehydrate. And then you have to compress it at 150 atmospheric pressure. That's what is needed usually for transportation and to storage. But if I'm tying CO2 capture with something else, making polymers, putting it into bioreactor, should we really need 150 atmospheric pressure? Do we really need that high quality CO2? So that what is the criteria for CO2 as a feedstock now changes the way even we think about CO2 capture. That's a whole new area of thinking we should put it in. Another thing is a scale of different options. If you look here, there's a liquid fuel, very tiny bubble. At the same time, let's see, carbonated beverage is large just because how many characters are there. But in real life, the market size is very different. So McKinsey did a study in 2016, and this is the updated version published in 2020 in June. Very nice data. They projected by 2030, this is how much CO2 storage and utilization we will have. Interestingly, we don't have as much storage because storage should be a lot bigger than this, but that's what they're projecting. But somehow or another, utilization is not so bad. You can put it into fuel. First of all, we can do enhanced oil recovery. This has been done already economically, and you can basically inject CO2 to take out more petroleum out of the ground. And unfortunately, right now, enhanced oil recovery reuses 80% of CO2 used in these technologies are natural resource. People kind of don't know that, but there are a lot of pockets of CO2 already well stored by Mother Nature. So the fact that we have to go back and mine those CO2 and using it to get more hydrocarbon out of the ground, that's not very good. So one of the low-hanging fruit we should do is an EOR using capture CO2. But they also look at these other technologies with a quite large bubble. You can make fuels, plastics, chemicals, biochar, and even construction materials. These are the big areas a lot of people are working in. So if you look here, going back, construction materials are usually in the bucket of mineralization and carbonates. This kind of goes back to what Rachel was talking about, the industry, steel industry. I'm working on this area quite a bit as well because, not because I was interested in steel industry, I was very interested in carbon mineralization for carbon storage. Because you can have magnesium silicate minerals or calcium silicate mineral react with CO2 and make thermodynamically stable solid, which we don't need to monitor forever in geological formations because these are thermodynamically stable solids. So I was very interested in terms of solids, the CO2 storage. But similar chemistry can be used to address the CO2 emission issues in steel plant, which we didn't know. So we start collaborating with steel plants. So if you look at the left-hand side, steel plants emits a lot of flue gas with the CO2 and of course waste gas as well. That's what Lenfest is using. They also have a lot of waste heat. There was a Q&A about that. And another thing they have a huge amount of is a solid waste. And interestingly, these solid waste are alkaline materials. So when you put alkaline materials with CO2 together, they actually react quite well. So we started designing this technology so that we can mix these three waste streams and actually make not only construction materials, which is much more sustainable, but we also recover minor materials like rare earth elements, and also make a precipitated calcium carbonate as paper fillers and plastic fillers. There are a lot of material sectors we can go into. It's interesting in China that this technology is being commercialized and we are part of it. The reason is they don't really care about CO2 yet. They hugely care about solid waste. So how to deal with solid waste is an issue because this particular steel plant we work with is not even one of the big ones. It's like a number 13 or 14 in China. They produce so much slag and then they utilize as much as possible already, but they are still filling up 1/3 of the Tribeca in New York, like every 4 years. This is becoming such a big problem with solid waste. They're looking at how to address this. This is one of the near-term CO2 utilization potential with even having some permanency. But we also have a big ticket item here, liquid fuels and chemicals and so on. How to get to these materials. We knew how to make these for a long time, but because the carbon dioxide is really low in energy level, pushing them back up to high energy level chemicals and fuels is not very easy. So we were waiting until we get carbon-free energy to do that conversion from low to high. So we thought it would take a long time, but luckily you see all these reports on negative electricity price in California a couple of years ago, and you even see all these reports saying that renewable energy will be very cheap and already cheap quite often depending on what and when time of the day and then during winter versus summer. So until now, the discussion on carbon management versus the renewable energy was kind of one or the other for a long time. But it became quite interesting as our renewable energy installation rapidly went into the grid because renewable energy start having challenge of energy storage. They start to see this excess electricity. But regardless that, you should not develop whole new business or new industry based on that negative price of electricity because we will have energy storage one day. But having said that, it became quite interesting synergy between renewable energy and CO2 area because renewable energy wants high energy, dense energy carrier. And we know that hydrocarbon or carbon bearing materials holds a lot of energy. So people start looking into, let's have a good catalyst to putting renewable energy into work so that we can store renewable energy into carbon bearing materials. But what people also forget to think about is they always assume we're gonna get magic hydrogen from somewhere. Unless you're making biochar or only making CO, CO2 has only carbon and oxygen. You need to have a hydrogen. So when you really look at holistic view, you need to also think about carbon footprint or energy footprint of hydrogen. So these days we are talking about 4 different colors of hydrogen, black, gray, blue, green, and depending on the color, it will make huge difference overall, whatever material you make. So what is the vision for the future? We hope to capture CO2 from wide range of sources instead of just doing power plant, ambient air, all the way to steel manufacturing plant, cement plant, or that so on. We want to combine CO2 capture with conversion for sure. So that there's a lot of interesting fundamental questions we have to ask. If you combine capture to conversion, what are the new challenges? The reason we are very interested in CO2 conversion using electrochemically because we can use electricity directly. One of the challenges in this area is that CO2 solubility in water, which is electrolyte, is very low. So you can boost it up by using our materials, by adding water lean solvent or other chemical additives, which is binding to CO2. So you can actually not only boost up the concentration of CO2, that material might hold CO2 on the surface of the catalyst just right that we can even have a cold catalytic effect. So in summary, what we are kind of envisioning is this. Hopefully we'll complete the carbon cycle, but in order to do that, we may or may not be able to do it in single step. General consensus is that capturing CO2 from wide range, including ambient air, will be challenging. We need to work on this. But at the same time, that CO2 capture material is providing CO2 to the surface of the electrocatalytic material, that will be challenged. But also CO2 to C1 compound or C2 maybe is maybe better with electrochemical conversion, but C2 plus product, as you saw from LanzaTech presentation, biocatalyst might be good. So connecting all these dots and then make a decision with the systems engineering and modeling and economics and policy all together to make the right platform molecule will be really important for the future. Since I discussed all these, I'm not gonna go through this, but basically we need new pathways to existing chemicals, but even new pathways to new chemicals for the future. And we need to include environment within our system boundary. These are funding agencies. I want to leave with a quick question, simple question, I think. Jet fuel from crude oil versus jet fuel from CO2, hydrogen, and renewable energy. Which one is better for the environment? Okay, how about easier question? Paper cup versus plastic cup. I hope you understand this is not a very simple answer, but something we really need to deeply care about. Thank you.
Thank you, Professor Park. Very interesting talk here. Very, very nice. It's open for discussion. Do you have any first question from the audience? So let me break the ice here. Professor Park, you were talking about norms and you're positioning that as an approach for essentially two different tracks, if I gathered correctly. One was direct air capture, and you talked about a very nice technology where you are able to encapsulate it. And maybe you are able to fluidize those directly, or are you using some solvent, sorry, not solvent, but a liquid carrier with it to transport it? And once you have captured the carbon dioxide, what is your process for the next steps? Because you're clearly not going to leave it there. Mm-hmm. You want to sort of bind it somewhere.
Yes. So in terms of direct air capture, or just let's talk about encapsulated solvent in general. Mm-hmm. So when you have a liquid solvent, especially in direct air capture, you have ambient air coming in, and then it has to be in contact with the materials you're going to capture. So there'll be a lot of particles, you could have VOCs, there are so many other things coming along, and environmental condition is continuously changing. It could be very dry day, it could be very rainy day. All those are big challenges when you try to capture from environment. Similar challenges exist in the point source capture as well, but especially in direct air capture is very challenging beyond even having low concentration. The good thing about these materials is that it doesn't evaporate, so it will stay intact. That's what's important. Another reason we wanted to encapsulate is to protect these NOMS materials or anything. We also encapsulate MOFs, metal organic frameworks, and other nanocrystals as well that protects. But one thing you should also know that CO2 capture materials loves water. A lot of times they love water. So what happens is if you leave these materials in the stream, it could be point source or direct air capture with a lot of water coming in, you will load up a lot of water, and that will have energy penalty during the regeneration because you have to put enough energy to evaporate all that water during the regeneration. Right. So we were hoping that having that encapsulation, we can selectively reject water and only let CO2 in. That was one of the reasons we did it. Another thing is the direct air capture, one of the challenges will be pressure drop. Because you have to move a lot of air through, you can do fluidized bed because these materials are very light. Density is like close to 1, so that you can, it's almost like a styrofoam in the system. So you can have a kind of a loose mesh of a cage, and then we can avoid these particles, and then you let the air through, and then you can have maximum contact with the minimum pressure drop. That was another benefit we wanted to have. Another design we have is we not only do encapsulation as sphere, we also have coaxial fiber design. We just got funding from DOE on this, on direct air capture. By doing so, you almost like design furnace filter-like. You don't want this to be really high pressure drop. Low pressure drop filter system, we can put it directly in the air, but bring it back in. And the question becomes, if you want to combine CO2 capture with conversion, how do you want to regenerate? And one of the things is that if you can regeneration is pulled by subsequent reaction, that's good. So we can also regenerate into the liquid system and then feed it to biological system if you need to. So that's one of the areas a lot of us are thinking about.
Okay.
Until now, most of people are looking at thermal regeneration, and that's the old way of thinking. Now, how to deliver the energy of bound CO2 and then put that to the catalyst surface closely, and that will be the maximum energy benefit, because you're not going to go from dilute CO2 to capture and another set of gaseous CO2 and go back into the absorbed onto the catalyst and then
Correct, yeah.
So if you can bypass the second well, I think it will be a huge benefit.
Perfect. Yeah. Thank you. Yeah. Are there any other questions? So let me ask you another question. Have you looked at the techno-economics of this particular approach? It's a very interesting approach, and I do believe it is flexible in the sense because you have also talked about the electrochemical, use of norms for electrochemical.
Yes, yeah.
To capture. So have you looked at the techno-economics of the whole process?
So we never really did the TEA because I'm not really good at it. I always want to get a industrial partner to do it better. So right now we are talking to Total, and then they are hoping, and also EPRI. So we are hoping to get TEA done. But in order to get to that level, first what we did was the recyclability of solvent, because that changes a lot in TEA.
Exactly.
Because if it only lasts 10 cycles versus the 10,000 type cycle, that makes a huge difference. So we are looking into that quite a bit. So we'll see how it goes. And in terms of even energy savings, heat capacity is one of the first thing we look at, because the binding energy is same if you're using same functional groups, but how much energy required to do the temperature swing is a big deal. And our heat capacity is not even half, like less than half of water. So we do have a huge energy saving in that too. But you need to do a lot of heat integration in a smart way. And if you're now combining capture to conversion, the TA becomes very complicated. So we don't have a good number yet.
But I think the approach is extremely innovative and really on the right track in terms of how to develop a system which is multifunctional in that way. So,
thank you.
Yeah, thank you. Really nice job. So I think with that, I guess we'll just clap. Thank you very much. We'll move on to the
There is one more question.
Oh, okay. Go ahead. Yeah.
From Alexander.
Alex.
Hi, I'm Alexander Navarrete, Karlsruhe Institute of Technology in Germany. I don't put the camera because here it's too late and I'm already in pajamas, so sorry. I was really curious to hear the Professor Park, really nice presentation about CO2 capture and utilization. And actually for us, it's really interesting that you mentioned the technology of Climeworks. So it was not so clear for me why, what is the difference between your technology and the one of Climeworks with the design with this, with these blowers. We have it here actually installed in the Energy Lab 2.0. Well, this technology is about the CO2 capture, then together with production of hydrogen and then synthesis of fuels is connected here. So for me, it would be very interesting this explanation and the comparison. And also you can make clear again the last part about the introduction of energy in the regeneration that would be advantageous. Thank you very much.
What is the technology you said you want me to compare to?
So between the technology you're explaining, your own technology and the one from Climeworks.
Oh, Climeworks. Okay.
Yes.
So there are, I think, kind of two groups of direct air capture companies, and Climeworks is actually one of the companies doing really well. They are really good at collaborating with the CO2 storage people and conversion people. So they really demonstrate their technology very well. Unfortunately, direct air capture technology has been developed not by government funding. Because for a long time, for 2 decades or so, people thought that direct air capture would distract people from doing point source capture, which we really need to do. Which is a very sad way of thinking, in my opinion, because we became academic because we want intellectual freedom, right? So I didn't think it was the right way to do. We should search for all the options, but unfortunately, they did not get a lot of funding. So most of the direct air capture technology were developed with the venture money. So then they didn't share a lot of information. So there are only a few companies, but they're doing really well because they developed this for decades. What they're really good at is moving air around. I don't work on the device building, and most of us working on CO2 capture materials do not build these modular design of fans, which has to be designed very well to effectively move a lot of air, because the amount of air you have to run through to get 1 ton of CO2 is huge, because if we're talking about 400 ppm. So now I'm actually collaborating with ClimateWorks and discussing this, because now what they have to do is to talk to all the people who've been doing CO2 capture in point source. Now I'll give you a harder challenge with the 400 ppm. Can you make your material to work in my system? So their material is okay, but I think their materials still have long-term stability and degradation, as well as selectivity and many other things. They can be improved. So now this is the new kind of era. Even DOE is funding for new type of direct air capture materials. So all the CO2 capture materials people are trying to apply and go to the much harder, harsher condition to capture CO2. So I think there's more synergy than competition, because we opt for something very different. Hopefully that answered the question. Well, and regeneration-wise, the energy-wise, we've been doing only thermal, but now people are looking at, can we do microwave or plasma or many other options? Like, can we deliver the energy differently? Because at the end of the day, let's say you have complex system, like NOMS, for example. The only energy you want to deliver is where CO2 is found, where carbamate is. So if you can only target and then only put the energy there, but nothing but, so that you don't heat up the air, you don't do any of that, maybe that will be the least amount of the energy input. And we couldn't do it until now because we did not have carbon-free energy like electricity, but now we have, or we are getting there, we can do this.
Yes, actually, microwave would be an excellent way. I would say, if you functionalize the material properly.
Yeah.
Thank you very much.
No problem.
Yeah, thank you, Professor Park.